5. It basically asks you to calculate the total fraction of histidine with a side chain protonated at a pH of 7.3. There's two major concepts that is involved in approaching this problem. First, you need to have a decent understanding of acids and bases, as well as how amino acids behave under those circumstances. We know with amino acids they have a basic functional group and they have an acidic functional group. So as a result, you'll have multiple pKa values depending on the pH of the solution. So the first thing you're going to need to think about is which pKa value to use. And remember, pKa value demonstrates the range of the buffer capacity of a given amino acid. So if we're working with a pH of 7.3 in solution, we're going to want to pick the pKa value that's closest relative to that range the amino acid is in. And the way you can usually figure this out is by taking a pKa and adding a plus or minus 1 to it. So, for example, let's just take pKa of 1. We find that it has a buffering capacity of 0.82 to 2.82. And that's nowhere near the functional group we're going to be needing to work with, since we're working at a pH of 7. So let's try pKa2 of 6. We have a range of 5 to 7. And that's pretty close, considering pKa3 will be 8.17 to 10.17. So we can expect the buffering capacity of histidine to be using pKa of 2. So this is the one we're going to be using. Okay. After figuring out which pKa value you use, we're going to need to go to the Henderson-Hasselbalch equation. Every buffer problem requires Henderson-Hasselbalch. So starting that off, it's pH equals pKa. And this time we determined it's 2, right? Plus log of your base over your acid. So, using what we know already, we know the pH is going to be 7.3, and the pKa is going to be 6. And doing some simple algebra, we subtract 6 from 7.3 and we get 1.3 equals log of the base over the acid. And using a simple log rule, we can figure out that converting logs to the exponential form, we get it to where it's 10 raised to the 1.3 power is equal to the base over the acid. And you'll have a calculator when you're working through these problems on the exam, so it won't be as difficult as this. This is going to be basically 19.95 over the base, the acid. So knowing this, and kind of making it round off to 20, we can kind of say that, well, if for every 20 base molecules that we have, or 20 deprotonated histidines, we have only one that is protonated at the time. So basically we can say that we have for 20 deprotonated over 1 protonated. Now you may be tempted to say, well, okay, so if we're just trying to find the fraction of protonated, it's just 1 over 20. But that's technically not correct. And the part of the reason is because we need to take into account the total fraction. This by itself is just a ratio. So what you need to do is, in order to have the proper number of atoms or molecules in solution, it's actually a total of 20 deprotonated plus 1 protonated. And that gives us 21 total molecules of histidine in solution. So really it's 1 protonated histidine over 21 total molecules of histidine. And so that roughly becomes 4.95%. And so roughly 5% of your solution. So remember, going back through these sorts of problems, the two big things you need to know is identifying your pKa that you're going to use and the Henderson-Hasselbalch equation. From there, you definitely will be able to figure out ratios of bases and acids, as well as pHs or pKa's of acids as well.